Okay. Welcome everybody to another MCRN Colloquium. Today we're very lucky to be joined by Dr. Hajo Eicken, who is the director of the International Arctic Research Center at the University of Alaska Fairbanks. I've known Hajo for a few years now. I first met Hajo in 2011 when I was lucky enough to go up to Utqiagvik Barrow and do some work on, well, it used to be called Barrow, Alaska, now Utqiagvik. I think I said that right. To do some field work as a part of my graduate studies, measuring fluid flow through the sea ice. So that was a great experience, and I've met Hajo a few times here and there on the sea ice since then, and every time it's been a pleasure for me. And so I'm very excited to have him talk about some of the current challenges in the Arctic and how we can meet them. He's been a leader in sea ice and Arctic research for a very long time. And so with that, Hajo, please take it away.
Yeah, thanks, Christian. Appreciate the opportunity. Good to meet and chat with this group. Just as a way of background for the presentation, this is something that originally I had presented to a group of math graduate students who visited here for a summer course that Christian was part of. I just want to make sure you understand, what I'll be talking about today is sort of at a fairly general level. I won't be delving into any details. But I thought, or so did Christian, that it might be worthwhile to sort of give you a bit of a perspective on where we sit in terms of broader research challenges in the Arctic. Originally, Christian had asked for a talk sometime in the fall, and then I said, "Oh, I'm busy, I can't do it. Then let's move it." Now that, as I reflect on what's going on with the Arctic right now, maybe I should have given the talk in the fall and would have had a bit more of a benign backdrop to some of what I was going to talk about. But maybe we have a bit of time at the end for broader discussion about kind of the current geopolitics of the Arctic as well. So what I was hoping to do is, as I said, I'll really just briefly cover what I see as representative challenges from a research perspective, specifically looking at this through the lens of disruptive climate change underway in the Arctic. I'll give you sort of a few examples related to permafrost, the ocean's sea ice cover, and marine ecosystems, mostly to highlight key aspects of the types of changes we're seeing in the Arctic. Some, or maybe all of you, may be really familiar with that already. So if at any point in time you feel, well, you either want to know a bit more or you want to know a bit less, feel free to jump in as well. This is a pretty small group, so I don't mind interruptions. I can't see you on the screen right now the way the presentation is set up, so you may have to holler. And then the second part of the talk, I just wanted to also briefly talk a bit about, well, what is it that we can do about some of these grand challenges? How do we respond to them? And again, just from my personal research perspective and our research center here at the University of Alaska Fairbanks, share a few examples of ways in which we can be responsive through research to some of the challenges that we're seeing in terms of rapid Arctic change. And then just very quick conclusions. So starting out here just with a bit of a reality check. Again, you all are probably very familiar with this. As you're aware, last year was the third warmest year on record. Here's the summary that's part of the European Copernicus consortium, showing both the global annual surface air temperature anomalies since the late 70s. You also already see, right, that in terms of the spatial distribution, a lot of those anomalies are highest in the Arctic and in the Antarctic. That's also clear here on the right-hand side. And so from the perspective of larger scale climate policy and climate action, it's clear that we're not going to be limiting global warming to 1.5 degrees centigrade, as had been the hope even a few years back. If we look at current politics, in particular for policy, that's an increasing unattainable goal. I'd like to ask, or ourselves, this group here, well, what does that mean for the Arctic, both in terms of the changes we're seeing in the Arctic, and then what are some of the impacts of that? And in that context, of course, we have to consider the fact that if we're talking about, say, 2 degrees centigrade warming in terms of global averages, we are committing the Arctic to a warming of well above 5 degrees centigrade. Why is that? Again, you probably all know about this polar amplification of global climate change through a variety of mechanisms. In the Arctic, recent work has it fairly clearly established that this is on the order of a factor of 3. Here's a study that came out a few years back here by Rantanen and others that also nicely showed how in some areas you see consistent temperature trends that correspond to a local amplification on the order of a factor of 5 to 6 or more. And that's important also from even from a geopolitical perspective, because as you look at these areas, you notice that in particular here north of Siberia, there's substantial disproportionate warming. I think it's also important for us as a reminder, although I'm sure everybody in this meeting is very well aware of this, that of course, if you look at this in terms of saying, okay, over the course of the industrialized era, it's been greenhouse gas emissions that are responsible for this outcome of committing the Arctic to substantial warming, that at least up until now, cumulatively, we here in the US have been the largest total emitter. I think that's an important point to just keep in mind. So what does that mean at the global scale? There's a number of ways to look at this. One framework that I find quite useful and very applicable to the Arctic is this concept of ecosystem service or environmental system services, meaning that there's a range of different benefits that we derive from the climate and the Earth system that we do not pay for. And it's important to there's a lot of discussion about the importance of monetary ways of looking at the world. I would really strongly always emphasize that in terms of the Arctic, in terms of the Earth system, Earth climate system, it's really not the monetary aspects that matter as much as some of the other factors. And at the very opposite end of the spectrum of thinking about the world, you might think about this in terms of cultural services, which, to be sure, some people are willing to pay quite a bit of money for, to be on a cruise, as you see here down in this bottom photograph in parts of the Arctic. But of course, we know that large parts of the Arctic population are indigenous peoples whose entire livelihoods depend on the services the system provides, including cultural services. On the global scale, of course, the Arctic is as well as the Antarctic, are major regulators of the global climate system, and of course, major regulators of global sea level. And those are important services or functions to keep in mind as well. This one here, this slide is a bit of a leftover from the presentation I gave to the summer school, but I did want to, in thinking about a group like yours, Math Climate Research Network, what are some of the important roles that mathematics and thinking about the world in terms of mathematical concepts can play as we think about rapid climate change and a changing Arctic? And I find this concept of tipping elements or tipping points in the Earth system to be interesting in that context. It's of course not universally accepted that that's a good way to think about some of our climate action, and I'm also a bit of a divided mind about this in terms of using this as a way to communicate key aspects of the climate system. But at the same time, this way of thinking about changes in the Earth system, transitions in key state variables or in system states, has caught on with the broader public. and is used in some areas already by policymakers. So, for example, the Scandinavian nations have their own sort of regional planning at a governmental level, and they're using the tipping points and tipping elements concept as a way to plan for long-term climate risks in Scandinavia. So it's not something that we can completely ignore. And if you're more interested in this, Timothy Lenton and others, of course, have championed this. If you visit the Global Tipping Points website there, you'll find plenty more quite informative work on this topic. But the reason why I brought this up is that if you think about tipping elements or tipping points in the climate system, where you have, through either internal variability or external drivers, transition into a new state in some form of irreversible fashion, then the polar regions are of disproportionate importance. And one of the classic examples of tipping points in the Earth system is, of course, the Greenland ice sheet, shown here at the left. This is from a paper by Andy Ashwan and others. Shown on the left here is the current configuration of the Greenland ice sheet with the different drainage basins. And then shown on the right are the configurations of the Greenland ice sheet as simulated by the parallel ice sheet model, or PISM, for different greenhouse gas forcings. Now, this is a slightly older paper, so these are still representative concentration pathways. So on the right-hand side, RCP 8.5 is probably something that is unfortunately quite realistic these days. And you see that you have, under these conditions, for an ensemble of 500 different simulations with the PISM model here, basically complete absence of the green ice sheet by the year 3000. So this is a long time scale, but it's a really important way to think about Greenland in many respects, including what we're seeing happen in Greenland right now in terms of the environmental processes. I find this also a great example because PISM, the parallel ice sheet model, is a collaboration between mathematicians and glaciologists. It's an open source model, maybe not as much in use in North America, but used quite a bit in Europe and Asia. And if you're interested in this, again, visit their website and look at some of the work that Andy Ashwan, as one of the key leads for this, has done. Of course, if you look at the picture here, Greenland year 3000, so those types of changes are irreversible on timescales under consideration here. So that's a classic example of a tipping point. The other thing I just wanted to highlight in the context of ice sheet models is, and this is a more recent paper by Andy Ashwan and others that's gotten quite a bit of use in the glaciology community, or the ice sheet modeling community, and that is that the way these models are configured, there's still quite a bit of work that can be and needs to be done to improve model physics, including getting help from mathematical physicists or mathematicians. What you see here at the top is just for the historical period, the last couple of decades or so, the cumulative mass change over the entirety of the Antarctic ice sheet at the top and the Greenland ice sheet at the bottom, and then the model projections. This is for a 2015 reference horizon out to 2025, and you see that these are all the models that are part of the ice sheet model intercomparison project, ISMIP 6, and you see that there's quite a significant bandwidth here in terms of the range of outcomes that these models, just for the historical or near-term time period, predict. And if you look at the right-hand side, you'll see that in terms of sea level rise contributions, that's also significant uncertainty there. So there's a lot of work that still needs to be done in this area, in particular with what we're seeing now with some of the behavior of these key outlet glaciers, both in Greenland and in the Antarctic. So to kind of end this introductory part of the talk, just a brief reminder then also, if we find the concept of tipping points or tipping elements in the climate system useful, they are useful in the context of Arctic science. There's different ways in which you can count these off, but it is in fact the case that the majority of global scale relevant tipping elements in the Earth system reside in the Arctic or the Antarctic. So from the perspective of thinking about the importance of the Arctic in a global context, there are substantial arguments to be made through this idea that there's processes underway in the Antarctic and to some extent, in the Arctic and to some extent in the Antarctic as well, that would have global repercussions as they play out and force the Earth system into a different state. And the examples that I'm showing here, these 5 tipping elements, the ones that I'd like to focus on a bit more today are permafrost thaw, Arctic sea ice loss, and I'll briefly also touch a bit on boreal forest fires, and you've already seen a bit on the Greenland ice sheet loss. I also want to point out that here at the International Arctic Research Center, we have researchers who are involved in research into all of these 5 tipping elements in the Arctic. So now let's look at this in a bit more detail here with these 3 examples. I'll talk first a bit about permafrost degradation, then sea ice loss, and then marine ecosystem restructuring. So permafrost is an important part of the Arctic cryosphere. If you look at this map here, you see that there are large parts of the Russian Arctic or the Eurasian Arctic that have continuous permafrost, meaning that below a seasonally thawing layer of a few decimeters or so depth, the ground below is perennially frozen. If you go to, for example, the North Slope of Alaska here, that perennially frozen part of the upper part of the Earth's crust, if you will, extends down several hundreds of meters in depth. And then I'm located in Fairbanks here, so roughly where the dot is, we're in the discontinuous permafrost zone. So ideally in those areas, you want to build your home on a south-facing slope in a aspen forest that's well drained, so you know that there's no permafrost underneath there. But if you can't afford buying property in those areas, then you end up in the low-lying lands where you will have very extensive permafrost throughout. And of course, those discontinuous permafrost zones now are also experiencing some of the most disruptive changes in terms of permafrost degradation. So if we talk about permafrost degradation, what are we thinking of? Here's a cross-section of a typical permafrost landscape, be it in Alaska, here, interior Alaska. This is out of a publication that our research center here released a few years back for the Yukon Flats. If you visit the web link here, we have a bunch of other reports on the state of Alaska's environment and climate that you might find interesting if you're working in that area. So in terms of permafrost degradation, the issue is that you have an upper layer of the soil that thaws out seasonally. As it warms, that active layer may reach down deeper and deeper as the ground underneath warms. And then you have areas where you have lots of solid ice with just a bit of sediment buried in the ground. And as that starts to melt and the overall permafrost thaws out, you find that the ground can slump. You find that in some areas you form these shallow lakes that then further enhance the warming. So there's a lot of landscape changes associated with thawing permafrost. And of course, keeping in mind that, as mentioned earlier, if you look at the surface air temperature trends in the Arctic, a lot of these changes are in fact focused on those areas that have continuous or discontinuous permafrost. So it's an important aspect of the terrestrial system in the Arctic. I did want to briefly mention that, I mean, permafrost is a very complicated stuff. But the permafrost degradation that I just described, it's important to recognize that strictly speaking, does not correspond to a tipping point or a tipping element in the Earth system. There's a very nice paper by Nitzbahn et al. That came out a couple of years ago that illustrates that very nicely. The key figure here on the right, that for all the different types of permafrost, 3 different sort of manifestations of permafrost thaw and degradation are shown on the left here, where, for example, you have the so-called thermokarst lake formation, where you have these bodies of water that form on the surface of the permafrost and then penetrate deeper and deeper, or these hill slope processes where you have these big slumps as the ground thaws. But for all of these different processes, Nitzbahn et al. Found that for increases in global mean surface temperatures all the way up to 4 or 5 degrees centigrade, there is a linear response in terms of the lateral extent of permafrost. So in theory, as you reverse some of these changes, you may be able to reclaim some of this. Although, as you can imagine, moving from a lake landscape back to a lake-free landscape does take time. But the other key aspect of permafrost is that it's a large reservoir of carbon, and unfortunately, a lot of that carbon is actually present in the form of methane, such that in recent years there's been a lot of new discoveries about the various ways in which methane can leave degrading and thawing permafrost, and some of these mechanisms hadn't really been fully appreciated in their importance in the past. And the study by Nitzbahn et al. Also looked at projected permafrost carbon release as a function of increases in global mean surface temperature. And then on the right-hand side, you see this translated through feedback processes into sort of a corresponding increase in surface warming, where this release of methane in particular, or carbon in general, does contribute significantly to the increase in global greenhouse gas forcing overall. So that's an important aspect as well. And in terms of now already starting to put ourselves in the mindset of, well, what do we do about that? There's an interesting development recently here in Alaska that I just wanted to highlight, more because it demonstrates an important principle, not so much that it actually does already have significant impacts. This is a bit of a busy figure, but if we just look at this here at the center, these are the representations of carbon locked up in soils around the world. So that's well over 2,000, probably up to 3,000 gigatons total. This is the amount of carbon locked up in fossil fuels that are currently discovered or known. And then you see that the total carbon reservoir in permafrost, even though area-wise that certainly is much less than global soils, is substantial, same order of magnitude, certainly as fossil fuel reservoir. And interestingly, about a quarter to almost up to a third of all that carbon is locked up in what's called Yedoma, ice-rich permafrost. Here's a photo on the left that shows this type of ice-rich permafrost, where as the permafrost degrades, you see, at least behind this like moon type landscape, where you see that as these ice-rich portions here, the ice turns into water, soil and the upper surface here loses its structural integrity, and the whole thing just slumps, but also releases in the process a lot of methane. So in Alaska, every summer we get these large forest fires, and their frequency has been increasing in recent years. You see this here in the plot on the bottom right. Those forest fires are, with increasing heat and intensity of these forest fires, unfortunately, a very effective mechanism to trigger exactly this type of process that you see here: permafrost degradation, melting of ice in the ice-rich permafrost, and release of methane. And so last year, the land managers, the federal managers of the Yukon Flats region here, interior Alaska, were able to elevate the protection status of ice-rich permafrost, Yedoma, to a level that's almost as high of protection status from wildfire as communities, such that we don't run the risk of losing disproportionately much methane from these ice-rich portions, which would represent a further amplification of greenhouse gas forcing. To me, that's a really interesting kind of policy instrument that's been put in place. It was put in place through intense discussions also with indigenous peoples in the region. The interior Alaska Dene, Athabascan tribes have a long history of managing fires, and their past management and stewardship actually was also in many ways designed to keep permafrost carbon in the ground. So they have both expertise and interest in this issue. The other key piece, just a brief reminder here, is that in Alaska, places like Alaska, a lot of our infrastructure sits on top of permafrost. Close to 4/5 of our highways are underlined by areas that have more than 50% of permafrost in the ground. Roughly half of our communities are in the same position, underlain by roughly 50% aerial extent of permafrost. So this is a major factor in terms of Alaska having to deal with infrastructure threats as a result of permafrost degradation. So in that context, sorry, just looping back. So here, from a challenge perspective, right? You already see this interconnection between threats to infrastructure, threats to economic activities, threats to traditional lifestyles of indigenous peoples. What's the role of policy elements that you can, or policy tools that you can employ to buffer or mitigate some of these impacts? So permafrost definitely, both from the local to the regional to the global scale, will continue to be and probably increase in terms of being a major challenge in the Arctic and requiring action, not just research, but action. So now the other piece that I wanted to highlight here is sea ice loss. As you've seen, there's an aspect to the distribution of winter sea ice that is a potential tipping element in the climate system. And just as a brief reminder, in the Arctic, we're seeing large losses of summer sea ice across the interior of the Arctic Ocean. Shown here is just the September 2025 sea ice concentration anomaly. So these blue areas are areas that are open water, or were open water at 25 relative to the long-term mean. In the wintertime, much of the ice loss occurs along the margins here, Bering Sea, Sea of Okhotsk, and over here in the Barents and Kara Seas and parts of the western North Atlantic. So those changes in the loss of summer sea ice, of course, has major impacts from a climate regulation perspective. It's a major lowering of surface albedo that is important in the broader context of the Earth system. And of course, it also impacts communities around the Arctic as well. And you see this play into some of the conversations we're seeing now unfold about various perceived security challenges in the Arctic. So one of the projects that's been led out of our research institute here by Igor Polyakov for well over 2 decades now is the so-called Nansen-Amundsen Basins Observing System. And what Igor and colleagues out of a number of different countries have shown is that increases in both temperature and flow rate and position of warm Atlantic water throughout the entirety of the Arctic Ocean. So just as an illustration here, you see this distribution, a temperature map here, with blue being -1.8 degrees centigrade, so that's the freezing point of seawater, and warm being or red being temperatures warmer or at plus 0.5 degrees centigrade, you see that this warm water over the past few decades has started to reach up higher and higher into many parts of the Arctic Ocean. And the analysis of this data set by Igor Polyakov and colleagues has explained up to 1 meter of sea ice loss in the Arctic basin just in these recent years. Why does this matter? This increase of heat transport into the Arctic is a key aspect of potential threats to both the loss of sea ice in the winter, as well as impacts not just on the heat budget of the Arctic Ocean, but also on the nutrient budget. So increases in the amount of nutrients here, potentially changing Arctic ecosystems in the Arctic Ocean. And if you look at the sea ice concentration anomaly for October last year, so October 2025, you see these large areas of roughly open water that remain open now off of the Siberian shelf areas in particular. There's a question that some folks have raised whether this is the start of an impending significant reduction of winter sea ice extent in the Arctic. And one of the recognized tipping elements or tipping points in the Earth system is in fact loss of winter sea ice in the Arctic, not loss of summer sea ice. I just want to highlight two lines of investigation that tell us that this is something to keep an eye out from a research perspective. Paleoclimate data clearly show that for the Holocene, Pleistocene past, sort of the more recent geological history, for atmospheric carbon dioxide concentration of more than 700 to about 1,000 ppm, we did not have any ice in the Arctic Ocean, neither summer nor winter. A very different climate state with very different climate in the northern hemisphere and the continental land masses around the Arctic Ocean. Elliot Zipperman and Hankel here, one of the postdocs working with him, have shown in a sort of reduced complexity modeling framework that for CO2 concentrations of around 600 ppm, we may reasonably expect a complete loss of winter sea ice. So that's what this graphic here shows: reduction of the maximum yearly effective ice thickness to a value of 0. And I would encourage you to look at this paper, a really interesting study, and it's one of the very few that looks at this question of are we losing, or what's the threat of losing winter sea ice in the Arctic, which I consider to be a major threat if plausible within the within the next 50 to 100 years if we don't do anything about greenhouse gas emissions. They also in their paper already pointed to the policy relevance of this finding. So then finally, in terms of observed changes, just a very quick look at marine ecosystem restructuring or ecosystem restructuring. The example I want to use here is also related to sea ice loss. We've seen substantial increases in mean sea surface temperatures throughout the Arctic. This is a recent study by Bahardarian and others. But we also see what are typically referred to as marine heat waves, or extended warm periods over the course of summer, where we just have anomalously high surface temperatures. And in fact, the Arctic is that part of the globe where we see the largest increase in marine heat waves and sea surface temperature extremes. What are the impacts of those? One organisms that I see, or species that I see as an important indicator in that context, is salmon, or the different salmon species. If you look at the Pacific Arctic sector here, it's a mingling ground of different salmon species from both North America, Eastern Siberia, and Northern Japan. And it's by now well established that increases in ocean temperatures have led to a host of changes in marine ecosystems that have already led to declines in Japanese population of salmon. So you see this here with a peak in salmon populations around the year 2000 and then a precipitous decline. I was at a meeting in Japan last year where one of the presenters indicated that Japan may lose its entire population of pink salmon, which are actually supported through hatchery enterprises as well within the next few years as a result of this warming. In Alaska, if you look at the larger scale picture here, for 3 of our salmon species, we don't seem to, at least in this graphic, there doesn't seem to be an impact yet. However, the past 5 years, all of the indigenous communities along the Yukon River have not been able to fish for salmon because of what's now seen as a collapse of important, economically and culturally important species of salmon. You see this photo on the right here illustrates what happens. These are 2 chum, male and female chum salmon that don't make it past these warm water areas, in particular the mouth of the rivers. So they, in this case in 2019, thousands of them died in front of key spawning areas where they never actually got into the river where they would normally spawn. And the graphic in the middle shows that, again, in the Bering Sea, we've seen record marine heat waves here in the past 10 years. So there's a clear causal link here between increases in sea surface temperature and some form of impact, which of course then leaves us, and that's what I want to spend the last 5 to 10 minutes on here with this question: what, if anything, is there that we can do about this? I want to emphasize that my take on this is looking at it from a local scale, right? We're sitting here in the middle of Alaska where a lot of this unfolds. We see our role in supporting the state of Alaska, Alaska Native tribes, other groups working internationally as well to respond to some of the challenges that they're experiencing as a lot of these services that the Earth system, and in particular the Arctic system, provides are being disrupted. I'm gonna do this very quick here to give us a bit of time maybe for a discussion as well. So one framework that is actively working towards being more responsive in a climate adaptation, mitigation, response space is this so-called Sustaining Arctic Observing Networks initiative of the Arctic Council and the International Arctic Science Committee. It's called SAON for short. And they have developed a roadmap for Arctic observing and data systems to be more responsive to societal information needs. And the way this has been implemented is through this concept of shared Arctic variables, where the priority for long-term observations is that they have to provide tangible benefits to communities in the Arctic, in particular indigenous communities, as well as to subarctic and non-Arctic regions. And there's a process in place that essentially tries to link the observing perspectives that are provided by global observing networks, such as those of, say, the World Meteorological Organization, regional observing networks, and then local networks. Typically, the greatest expertise, the greatest drive, the greatest insight sits with indigenous communities in the Arctic on that local scale. And I, again, real briefly, just want to highlight that there's a whole process within the research community and different governments who are pursuing this approach to help improve observing system inputs by linking them directly to specific societal benefits. The example that's given here is for various observations related to sea ice, and there's sort of a process, an actual web tool in place to do this. This is something that's been put together under leadership of Sandy Starkweather with NOAA, who also for a long time chaired the SAON board. It's supported through this through the U.S. Arctic Observing Network, and so there's a lot of different groups that are trying to get us to be able to better connect different observing system components to specific applications that directly translate then into societal benefits. The example I want to highlight in that context is related to salmon. The marine ecosystem restructuring example I just gave you, because it also illustrates, it's one thing to say, oh yeah, there's a government agency that's assessing these benefits. In the current political climate, it's as much about effective collaboration in terms of meeting these challenges as it is about having some framework or scientific tool or some cyber infrastructure in place to support these activities. And I just wanted to give you this example here, again, focusing on this concept of shared Arctic variables. I already mentioned briefly, right, shared Arctic variables would be observables that are relevant in an Earth system context, ideally from the local to the regional to the global scale, but they have to be translatable into information that's relevant in the decision-making or planning context where actual benefits can be derived. And so in many ways, a lot of us who are working in this space on shared Arctic variables also think about it as a way to establish communities of practice or collaborations between different groups, scientists, engineers, community-based observers, indigenous organizations, resource managers, policymakers, using these different approaches that you see outlined here, or aspects of a collaboration, with co-production of knowledge being particularly important and something that we here at our research center here at IARC are quite passionate about. So I mentioned I wanted to apply this to the example of salmon, and salmon is a great example because you find that people in Japan, including resource managers in Japan or Russia for that matter, have as much of an interest in the health of the salmon populations in the Bering Sea as do tribes and tribal communities, individual families that are extending out, for example, along the Yukon River here, that for millennia have traditionally subsisted on salmon and have also used this as an important source of income in these communities. So there is already a connection through this variable, if you think of salmon as a variable with a number of observables, such as the salmon population, the age range, or even associated variables such as the ocean temperature that they are swimming in. It's already connected, or there exist connections between a range of different groups, both interest groups as well as different people. And so our center here, with support from the National Science Foundation, is supporting an expert panel that brings together these different groups from organizations that may not always see eye to eye, such as, for example, federal fisheries managers, state fisheries managers, indigenous or nonprofit conservation groups, representative of the fishing industry. But we see this approach to put together groups of people around these so-called shared Arctic variables, such that these communities of practice can evolve as an important tool in responding effectively to challenges. And then the final thing I just wanted to highlight here before I end is at the same time, of course, you can't just rely on networks. You have to also provide effective decision support. Again, that's something that our center, because we're home to the Department of Interior Climate Adaptation Science Center for Alaska, the Alaska Tribal Resilience Learning Network, the Alaska Center for Climate Assessment and Preparedness, all these different groups that are part of our research institute here, IARC, help us advance effective approaches to provide decision support that's actually useful. And so the one example I wanted to highlight, we've got a whole slew of them, is this Northern Climate Reports tool, or northernclimatereports.org. That was specifically developed to share with anybody, but in particular, community or tribal planners, local government, but also the private sector, with actionable climate information for their particular region of interest. So if you visit the website, you'll get a whole bunch of relevant climate and environmental variables, both climate states as well as projections and additional information for all the different communities in Alaska, as well as any geographic coordinate that you enter. I'm just showing you a very small part of what this might look like. This is an example for Utqiagvik, right in northern Alaska. We talked about this earlier, where it provides a text summary, but it also shows here, for example, a projected loss of permafrost by the end of the century for different types of climate simulations. And so you can access both graphics as well as some of the underlying data. And the way this has been designed is to be usable without, or be usable by a range of different decision makers and planners at the community level, making it easy for them to integrate this information into, say, community climate adaptation plans, community hazard mitigation plans, or emergency management plans. So thinking more about the role of science communication, product generation is a very important aspect of all this work. With that, I just want to leave you here with these 4 points in terms of what to take away. Again, this question of tipping elements, tipping points, disproportionately important in the Arctic, if we look at it from a global perspective. So an important justification for why do we care about the Arctic. Complex system dynamics plays a key role here, and that's, of course, also where collaboration with mathematicians is very important. Same goes for improving Earth system models. I gave you the example of the ice sheet modeling component of Earth system models. And then the final piece here is that science communication is increasingly important. It's always been, but arguably now more important than ever. And I actually would argue that collaboration between climate scientists and mathematicians can add an important dimension to science communication as well. So with that, I'll stop the share and would be happy to take questions if we have time.
Great. Yes, thank you very much, Hajo. And that was a great and always informative talk, and find our clapping emojis there. Yes, we definitely have some time for some discussion. If anyone has questions, please go ahead.
Yeah, can I ask something?
Yeah,
Hi.
Chris.
Hi, this is Chris Jones. Let's see, at the beginning you talked quite a bit about tipping elements, and it also came up a lot during your talk. But I got the sense you were hesitant about it. You had sort of like mixed feelings about using that as a framework to think about some of these issues, or even considering it. And could you say more about that? If I'm right in detecting that? Oh.
Yeah, no, yeah, you picked up on that well, Chris. And I should say that personally, I still find them very useful as a science communication tool, because it's sort of the concept of translating potential energy concepts, say, or potential energy wells into how do you illustrate different states of the climate system? What does it take to move from one state to another? Is it a reversible, historetic behavior? I mean, all of those from a didactic perspective, I think are great. My hesitation comes from 2 points. One, in terms of climate action, on a political scale, there's been different approaches to communicate urgency, right? So there's the concept of planetary boundaries, that Johan Rockström and others from the Stockholm Institute have propagated. There's the concept of just saying, hey, let's put up a barrier. We cannot exceed 1.5 centigrade. Those simplify things, but the problem is that if they simplify things to the point that you're saying, well, okay, now we've crossed 1.5, what's the big deal? Yeah, some issues are, we have major issues in the climate system, but it's not like the world has ended, so let's just ignore everything. like the psychology, the cognitive psychology of people who are processing that information, in my mind, has to be considered as you think about, are tipping elements or tipping points a useful concept? And right now, out of those three examples I've given, I would argue they're probably the most sophisticated concept. But at the same time, there's also still confusion because, you hear a lot of people talk about, oh yeah, Arctic sea ice loss, tipping element. Well, no, summer sea ice loss is not a tipping element. It's not associated with a tipping point. That's well established now. Winter sea ice loss, for all we know right now, is. And so those nuances, I guess, at least we within the research community have to be very clear about, okay, what do we really understand this and how do we communicate it? That's it in a nutshell.
Thanks.
Okay. Any other questions, Rob? Yeah, Kate, I think I see you raising your hand. Go ahead.
Yeah, I'm curious if you could tell us a little bit more about kind of the process of forming coalitions with among like different stakeholders, and heard you say like kind of co-creation of knowledge is important at the center that you're at, and I'm just wondering, like, has that been, I imagine that's been something that's been ongoing. I imagine like kind of building those sorts of relationships take time. And if you can just talk more about your own experience with that.
Yeah, that's a great question, because I mean, my experience is that it's, as you say, it takes time. You have to build trust. And in particular, if you have representatives of organizations where there's a history of mistrust or misconduct, right? Or then that's even more difficult. So the way we're approaching this is that we're at our research institute, and with this specific example I gave for the salmon shared Arctic variable, try to create a space where it's clear to everybody that there's no discussion about, for example, regulatory action or the history, which of course, if you look at salmon, there's a nasty history of colonization in Alaska, that's kind of been perpetuated over the years. But there's also recognition that you have individual people, even within organizations, who may have a policy that is not in favor of certain measures, but you have individuals in those organizations that are passionate about what they do. They share values. That's really important. Do they share values with the other partners in these collaborations? And once you've established that, including my own work, I found that that's the first step to sort of build collaborations that help you transform and move past some of these challenges. And I want to give you a specific example, right? Because to me, that's one of the problems we have right now. Even if you look at Congress, right, or even state legislatures, a lot of people don't want to engage anymore, even at that level, and that makes effective policy making very, very difficult. So the example I want to give is, and this is now, 15 years ago, there was a big push in Alaska for offshore oil and gas development. The Inupiat of the North Slope, the indigenous peoples, were greatly opposed to a large extent, not all of them, but many groups greatly opposed. There were different perspectives from different levels of government, local, state, federal, and the key. So we, a group of us, organized as part of the International Polar Year, a meeting in Utqiagvik, a center of both opposition and discussion, and we brought together engineers from the oil companies that were proposing development. We brought together people from Norway that were working on similar issues in Norway, but in a very different political settings, and talked through over a 3-day workshop a lot of these challenging issues. And one of the things I took away from that was that, one, people in the community saw like these engineers not as these evil person who are trying to destroy their livelihood, but recognized that they have their own ethics, their professional ethics. and some of the values directly aligned with what the local community wanted. And they also saw, in particular from the person we brought in from Norway, who met with the entire community in a separate meeting. Nobody else from Alaska participated other than the community, and really conveyed, from what I understand to them, that you can, using Norway as an example, you can do both development and protection of, at least in the Norway interpretation, of your core values. So the bottom line is that, yeah, it sort of takes time, but it's important to find the right people and create, in particular, these communities of practice where you have this informal way of moving things forward.
Mm-hmm.
That was a bit long, but you can tell I'm passionate about this.
Yeah, thank you.
Okay. Any other questions? Yeah, Olivia.
Hi, thank you. That was a great talk. I've been trying to figure out the best way to phrase this, but I'll just go for it. So Chris pointed out that you maybe expressed some concerns about using tipping points as, I guess, this consistent talking point about Arctic issues, environmental issues, but you did also express a lot of hope and interest in having mathematicians collaborate with environmental scientists. You talked about complex dynamics, tipping elements. What are there specific areas that you see as potentially the most, potentially the most fruitful for collaborations between mathematicians and environmental sciences or environmental scientists, or areas where you see studies of nonlinear dynamics being particularly useful going forward?
Yeah, that's a great question, and I'm not sure whether I have a good enough understanding of the math to sort of pinpoint it. But I would argue that a lot of the discussions around tipping points, irreversible transitions in system state, and the associated dynamics, to me, those are really, that's already at a fairly high level, but that's very productive. And so to give you an example, right, because there's all this question about, okay, is like irreversibility matters a lot to policymakers. And it's always sort of implicitly, it's always, oh, everything is reversible, right? All we got to do is pass a law and boom, we're back to where things were. So communicating that clearly and communicating also, at least with select people, so now I'm talking about staffers in Congress or legislatures or other policymakers who are much more sort of on the technocrat spectrum, communicating clearly, how much of a heads up do you get about some of these critical transitions? So the understanding of, like, there's some recent work that I'm quite excited about, this whole concept of critical slowing down in terms of phase variables. Is there predictability embedded in that? How do you deal with uncertainty? The whole concept of Bayesian approaches or using Bayesian approaches to decision making, it's going to require more work, but that's also why I feel the communication piece is so important, because we got to move beyond sort of the really simple stuff if you want to have an impact. But to me, all of those areas are very promising, and that's where I feel having mathematicians in the room who are good communicators is critical. And I want to acknowledge, like, just getting back to Chris Jones's comment earlier, I'm definitely personally grateful for all the people who've developed these tipping point concepts or alliances, what have you, because it makes all our life easier. I'm not saying, oh, this was a bad idea, but we just got to be very, very diligent about how we use some of those tools.
Awesome, thank you.
Okay. Any other questions?
Thank you very much for a great talk. I really enjoyed it. Yeah.
Okay. I guess with that, we'll thank Hajo one last time with some clapping hand emojis, and I will go ahead and say see y'all next time.